on the closed interval. Okay, not a big surprise for us there. Let's go down and look at this one, though. The definite integral as the area of a region. Now again, we haven't actually found the area of a region using integration. We found it by breaking the area into rectangles and then summing up the areas of those rectangles and then taking the number of rectangles to infinity. Section 5.2, looking at the limit of the summation of the areas of those rectangles. Here it says that we could do the area with an integral. So let's see what we've got here. Function is continuous and non-negative on a closed interval AB. Okay, again, if it's continuous, then it's integratable. Then the area of the region bound by the graph. Now this is important here. We are going to be bound by the graph of a function, the input axis, and the vertical lines. What vertical lines have we created? Well, those representing the boundaries, the interval. Okay, so when we look at this, we're looking at, again, if we have something like this, if this is A, this is B, we're looking at the area in here. Okay, bound by the function. So here's f of x. What's the equation of that line? It's a vertical, so x equals a. What's the equation of this line? X equals b. And what is that line? Well, actually, it's f of x equals 0. Or if you want to, just y equals 0, otherwise known as the input axis. Okay? So we are looking at the area in here. And what we're saying is, if we want to know the area bound like that, we're going to be able to use our integration to come up with that. Why? Because integration, where's our comment here? Because the integration like that is the same thing as the limit of the sum of all the areas of all those rectangles if you take the number of rectangles to infinity. So there's the connection again. And so we're saying that if we want to find the area of a region, we're going to be able to use the definite integral. Okay, let's go on. These should not come as too much of a surprise, but let's just go through them. If the function is defined at a value x equals a, then the integration, now you have to take a look. If you can't see this, let me just highlight. That goes from a to a. From A to A. And it says that the area of the rectangle, so if I have this is f of x, the area of the rectangle that goes from A to A, what would be the area of that rectangle? Is there a rectangle? No. And so, you know, at most, I would end up with just that vertical line. That's not a rectangle. What's the area of that rectangle? It's 0. Okay? And that's what this is saying. So again, we're going to be now thinking, none of these is just indefinite integrals, antiderivatives, but now we have a real connection to them. They are areas under a curve. Now let me also share with you at this point that beyond just this geometric definition of a definite integral, the integration under a curve, we also, though, are able to find some applications other than this geometric one. And if you think about all of the antiderivatives, what we're going to do, and I've got one of these that will probably, we may get to it before the end of Thursday, but if we don't, it will definitely be in the lecture for a week from Thursday. Well, what we're actually doing is, if you can identify the antiderivative, and you want to know, you know, I know what the sales was on Monday, and I know what the sales was on Tuesday, and I know what the sales is on Thursday, and I know that the sales, let's say revenue of a store, I know what the function of that revenue is. Well, if I know the revenue from Monday and Tuesday and Wednesday and Thursday, I want to add up the revenue of all those days. What we can do is, if we know the derivative of the revenue function, the marginal revenue, then we can integrate, and this is the same thing as then adding up the functional values throughout all those days. And so we use the integration as a way of finding the sum of multiple values of the antiderivative. That's one of the applications we have for this. Okay, well, what about this? This is saying that, and I'll put this in different color. If we integrate from B to A, it's the same thing as integrating from A to B. So the A and the B are interchanged in position, but notice it's the opposite of that. So what we have then is that if we are integrating from A to B, and we want to integrate in that order from A to B is one sum, but if we go in the opposite direction, it's a negative. Now you think about negative velocity changes, means that you're going towards something instead of going away from something, so the same thing here. What we want is, we don't want to say that the sum of the sales or the sum of the revenue for the store is negative, just because I went from Thursday back to Monday instead of Monday to Thursday. So we take the opposite of that, and that then negates that negativism that comes out. Okay, so these two special ones, not too difficult if you think about it in a geometric way. Let's see what these are. Additive interval property. Okay. Let me highlight here so we can see. The function is integratable on 3 closed intervals determined by A, B, and C. It says that the integration from A to B is the same thing as integrating from A to C and C to B. Now, that's best understood if we think about it this way. There's A, there's B, and C is somewhere in between. If I take a look at this and I go from A to B, if I find the area of A to C and I add onto it the area from C to B, do I have the area from A to B? Yeah. Okay, so that's what this is explaining there. Okay. You know what we've done this all semester, haven't we? We get all these properties out. Then once the properties are there, then we can start looking at some problems because we can apply the properties. So here we go. This is one I don't think you really need a lot of explanation on. We have seen it before. F and G are integratable on the same closed interval. K is a constant. The functions K of F and F plus or minus G are integratable also. Take a look at this first one. Are you surprised? Same thing. We've seen it before. We saw it with the indefinite integrals. There it is again. You can pull the scalar out in front. So we could use that, if we need to. What about the second one? We've seen it before. Now we're just saying that it works for definite integrals too. Just because we have it on a closed interval doesn't make any difference at all. The integration of the sum or difference of two functions is the sum or difference of the two integrations. Okay? Not a surprise. We've seen them before. Okay. Preservation of inequality. Let's see what this has to say. If the function is integratable and non-negative on the closed interval from A to B. Non-negative. The function is non-negative. That means that all of the function lies where? Say it again, Erica. Above the input axis, yeah. So the whole function, remember, we talk about this a lot, and we're saying that, f, this would be the same thing as saying f of x is non-negative. The outputs are not negative. Could they be 0? Non-negative? Does that include 0? Is 0 negative? No. So it could be 0 or positive. So it says that if it is, so if all of the function output values are above the input axis, then the integration from A to B is also positive. Now, we have this thing about if it does fall below the input axis, then we have that the integration is negative. But here we just have this preservation of inequality stated in this direction. What I just talked to you about comes, I think, in section 5.6, and I don't get the opportunity to teach that to you. So those of you going on into Math 70, you'll get into those situations. Okay. F and G are integratable on a closed interval, A and B. F of x is less than or equal to G of x. Then for every input value in the closed interval, we have that the area under the curve from A to B of function f of x, which happens to be less than G of x, that area is less than the area of G of x. Let me illustrate here. And again, this now, what I'm showing you now, really gets us into section 5.6, which again, I'm not going to be able to get into much detail on, because that does come in Math 70. But let's just say this is f of x. And let's say that this is G of x. Would you agree that especially in that interval, that f of x, all the outputs of f of x are less than all the outputs of G of x? Okay. Would you agree then that the area under the curve, remember we're defining the area under the curve in section 5.3 to be that area bound by the curve, the input axis, and the vertical lines. So would you agree that that area is less than the area under the curve bound by the vertical lines and the input axis of this area? Okay, that's all it's saying. Okay, that's it. Now, what happens is, in section 5.6, is that what if you want to know the area between the curves? Think about it. You already know, probably. You could figure out a way to do that. If I want the area, I'll put it in this color here. If I just want this area, and I can determine the integration of f of x, and I can determine the integration of g of x, how could I determine the area between the curves? Subtract them, absolutely. That's it, subtract them. Actually, that is what happens when we say that it's bound by the input axis. If this is f of x, and let's say g of x is down here, we're really subtracting them. We just don't tell you that at this point. But yeah, we would subtract them. So this is, in preparation for that section 5.6, which comes up. Okay, let's get back to our notes. Where did they go? Here we go. Okay. Well, let's see. Sketch the region whose area is given by the definite integral from 0 to 4 of x divided by 2 dx. Okay, so the first part, just sketch a region, and then it says use a geometric formula to evaluate that region. I'm going to pause our recording right now. The problem with you guys, you know what the problem is?
You don't try.
Well, I wasn't going to go quite that harsh. I was going to say, you really try to make it too difficult, okay? You try to make it too difficult. But maybe you don't try. Okay, I'll take that.